So I want to give you a little bit of a sense of Ramanujan's work and the impact that it has, or the impact it's continued to have. And I'll try to talk about four different vignettes of his work, which is especially interesting to people working in my area of analytic number theory. And a couple of them will be absolutely his best work, and then one or two I chose for relevance to me as well. This is one of Ramanujan's early papers. This appeared, I think, in the Proceedings of the Cambridge Philosophical Society, nowadays called the Mathematical Proceedings of the Cambridge Philosophical Society, from 1917. And he was interested in a question which is very classical, going back to Gauss and Legendre and Lagrange. The theorem states that every number, every positive number, can be written as a sum of four squares. So you're allowed to use 0 as a square, and so you can take any number you feel. 2025 is too easy because it's just a square already. It's 45 squared. But if you take 2024, you can amuse yourself by writing it as a sum of squares. So, and Ramanujan was interested in this question of whether you can generalize this instead of just considering squares, x squared plus y squared plus z squared plus w squared, or u squared in this case. What happens if you generalize the quadratic form that you have? What kind of forms can you write which represent all numbers? What can you say about this? And in this paper, he confines himself to these diagonal forms where there are no cross terms, and he finds that there are 55 examples where you can prove that they represent all numbers. And he asks various other questions that he would like to answer in this context. And the paper makes for very interesting reading because he uses results which were known to Legendre and Gauss on representing numbers by quadratic forms in 3 variables and uses them to understand what happens when you add one more variable. But the reason why I bring up this particular paper is that it has a relevance to some work that I did and also to some work which is very beautiful work done by Manjul Bhargava. So there's a beautiful generalization of Ramanujan's work, and it says, it's this theorem which was first discovered by Conway and Schneeberger, and then a beautiful proof was given by Manjul. And it says that if you take one of these forms, like sums of 4 squares, you only have to check that it's true for the numbers from 1 to 15. If it is true for the numbers from 1 to 15, then it's always true. It's an amazing result. And I think Ramanujan would have been absolutely floored by a result of that type. And in this paper, Ramanujan had a remark about quadratic forms in 3 variables, which is a very mysterious subject. And he says, for this particular form, x squared plus y squared plus 10z squared, you can figure out what even numbers are not represented in this form, but the odd numbers, he says, do not seem to obey any simple law. So he found a bunch of odd numbers. There's no reason why they can't be expressed by this form, but somehow they are missed. And it turns out that there are 2 other numbers that are missed. The last one, funnily enough, is 2719, which is at least in case 10, a permutation of 1729. And then we think that these are all the numbers that are omitted by this form, and everything else is captured. This is a very interesting problem because understanding problems like this, it's an extremely difficult piece of mathematics, a very profound piece of mathematics. Only in the late 80s did people figure out when a ternary quadratic form represents all the numbers that it's supposed to represent. And this was done in a breakthrough work by Ivanets and then by Duke and Schulze-Pilot. And still, it's not a complete answer because there's something called Siegel zeros, which is something we still don't know how to get rid of, which makes this ineffective, that you can't actually determine all the numbers. You can only say all but finitely many numbers are represented. And then Ken Ono and I, about 25 years back, wrote a paper in which we figured out, at least if you assume the Riemann hypothesis, that we can solve Ramanujan's problem and get all the numbers represented by this form. Thanks, Tadashi. And with the last exceptions being this 2719. So there's a lot to this content. And okay, let me tell you the secret reason why I wanted to show you this, this particular thing. This is Manjul and me from 2005 when we got the Sastra Ramanujan Prize. And we are sitting in what would in Tamil be called the Thinnai of Ramanujan's house in Kumbakonam. This is the house where he grew up.
Sorry, what's Thinnai?
Thinnai literally means this place we are sitting. It's like a porch or a portico. So a lot of these old houses would have a place where people could sit and look out on the street or talk to each other. So, okay, so let me tell you a few other examples of Ramanujan's work. This next paper, which is on Ramanujan's tau function and the Ramanujan conjectures, is probably the most profound work that Ramanujan did. And I think its impact is really tremendous, and it's the kind of impact that could not have been foretold at that time. So I don't think it was appreciated in Ramanujan's time or within 20, 30 years after Ramanujan's death, the impact that this would have, and Brian will tell you a lot more about it. So this also, it's very unclear what Ramanujan's motivations were, but one of them is also in thinking about sums of squares. I told you that he thought about sums of 4 squares, going back to Lagrange. Gauss had thought about sums of 3 squares. Jacobi had thought about sums of 4 squares and finding a formula for it. Fermat, of course, thought about sums of 2 squares. So it's an extremely long list of all the great mathematicians who thought about this problem. And Ramanujan looks at the number of ways of writing an integer as a sum of 24 squares. So he did think about all other cases as well. And then when you think of the number of ways of writing an integer as a sum of 24 squares, he finds that there is a formula for it. There is one part of it which is kind of, in some ways, an easy thing to understand. That's this function sigma 11. It's a sum over all the numbers that divide a number n, and you raise it to the power 11 and you add them all up. So it's something like n to the 11. Then there are these funny numbers like 691 floating around. And then there is a mysterious object. There is this object tau n that comes up in this formula. It's an exact formula. There are no error terms here. And this function tau n is obtained in this by multiplying this product together, expanding it out into its series, and you get a function. And he computed a whole bunch of values of this function. This is in a paper of his, also in the Transactions of the Cambridge Philosophical Society, but I don't know much about this journal, whether it just became the Mathematical Proceedings later on. So he computes this all the way up to 20, and these are big numbers. I want to show you 2 things from this paper. One is, how did he compute these? And this will give you some understanding of the kind of things that he was interested in. So in this paper, he has a little section in saying how he computed it. And I found this very amusing to read this section because sometime last year, I had to compute something quite similar. There's an exponential of a power series, and I want to compute what coefficient you get when you multiply it out. And I wrote a computer program to do that. And I tried to do it by just expanding the exponential out. And my program took some time to execute. But I had a bright grad student at the time, Rodrigo, who was very good at coding, and he wrote a much better program. And the program he wrote would be essentially what Ramanujan does. So you don't try to compute by expanding out the exponential. You differentiate the exponential, so you know f prime over f. That tells you what this expression p is. And then you use that recurrence to compute the coefficients. So that's what he's doing here. And that's a much faster way to do it. And I guess if you're computing it by hand, you want to find a fast way of doing it. And then he notes the next thing that he notes is also very interesting, because he says, this has too many terms. If you do it by starting with the cube of this guy and then taking it to the 8 rather than taking it to the 24, then you can speed up the recurrence because you only need square root of n terms in order to do the recurrence. So his paper is filled with things of this type where, you say he computes this table, but how did he compute this table? And he kind of tells you what he did. And it's interesting. And the next thing that he says is this is the sheet where he talks about the Ramanujan conjectures. And this is an amazing piece of work, and it's incredibly modern. in its formulation. So this function tau n, he forms a series with this, which is kind of like this series for the Riemann zeta function. And he conjectures that it has product representation like the Euler product for the Riemann zeta function. It's completely unclear why he was doing it or how he was inspired to do this, because nobody else was doing it at that time. And so this is a conjectural expression. The conjecture is that these coefficients have an interesting multiplicative property, which is not at all obvious from the expression that you start out with. And then he says that if you write these values of the primes as cosine of some angle, which again, I'm not clear why he was led to that, then you have nice expressions for all the other composite numbers, the values of n. And then he's conjecturing that this value is an actual, it could be a complex number for all you know, but he's conjecturing that it's a real angle that corresponds to it. This is the famous Ramanujan conjecture. So I tried to look at the paper to see what his motivation for making this conjecture are, and that's also extremely interesting because he considers other analogs of this tau function called eta products, and he works out for many of them, he can actually figure out what coefficients you get, and he can verify his conjectures. One of them happens to be an actual object connected to an elliptic curve. So he doesn't make this connection with an elliptic curve, but it's kind of interesting that an example that he picks is something that would have to wait maybe another 40 years before people found a different interpretation for his example. This, I think, is probably his most important contribution to mathematics, and it keeps going. Within his lifetime, or just after it, what was appreciated as his greatest contribution to mathematics would be his work on partitions. So if some of you go to see the movie on The Man Who Knew Infinity after today's event, then you will see that this plays a key role in Ramanujan's story. And certainly, at the time that it was achieved, it was absolutely remarkable. So the partitions of a number are a way of writing it as a sum of smaller numbers. So for instance, if you take 4, there are 4 ways of writing 4 as a sum of smaller numbers. 5 ways of writing 4 as a sum of smaller numbers. But if you take a large number n, the question was, how many ways of writing n as a sum of smaller things? And nobody had a good guess for how this function should grow as a function of n. And Hardy and Ramanujan found a remarkable method which produced an asymptotic formula for the number of partitions. This is a simple version of the asymptotic formula. You can see it's kind of a rapidly growing function, not like exponential, but exponential in root n. And it has interesting constants that intervene. So nobody would guess, just based on the numerics, what this looks like. The method that they used to prove this also led to an enormous amount of mathematics. It was the first example of something called the circle method, which was then worked on extensively by Hardy and Littlewood after the war, when Littlewood came back in 1918. Now, in their paper, they actually did a lot more. They actually wrote down a much more complicated formula, which has this remarkable property that if you try to compute the number of partitions for 200, which is a big number, so a 15-digit number, they found an asymptotic formula which basically gave an exact answer. This is an extraordinary thing. One would think that a formula is very good if you get half the digits right. Like the Riemann hypothesis, which is about counting the number of primes, is a statement that you can get half the digits right. But how do you get all the digits right in a formula like this? That is an extraordinary thing that they managed to achieve. And this insight, Hardy says himself in many places, is really something that Ramanujan somehow believed in. And it's unclear why he believed in, that there should be an answer which is exact, and they actually found that exact answer. Now, I want to end by one last thing, which is a page from Ramanujan's lost notebook. So it's these were unpublished manuscripts which were given to Hardy and then were found in the Cambridge Library by Andrews, and people have looked at it over a period of time. I happened to look at this about 15 years back when I was at a conference in Florida. And then I found that this was something I just did not know about Ramanujan's work, where it intersects with something in multiplicative number theory, where he had some work, but not, these two things were quite unknown to me. So the first one here, he is interested in counting the number of integers up to x, which have exactly k prime factors. And he writes down, if you imagine that you take the exponential of log x, that would just be log x, and you're taking the series for exponential of log x and expanding this out. So this is just counting all numbers up to x, which is just x. So he says that if k is infinity, this is true. You're just counting all the numbers up to x, and that's x on the other side. And then it's known due to lambda and others that it's true when k is a finite number as well. And then he says this is true when k is a function of x. Now, this is in Ramanujan's handwriting. This note here is actually in Hardy's handwriting. And he says there's a reference to a paper of Hardy and Ramanujan where they prove something along these lines. But what Ramanujan is asking is something much more precise than what's in this paper. And that was established really in work of Selberg sometime in the 50s. So, but I'm not sure anybody was aware of this question. This one is even more remarkable. He is asking about the number of integers up to x, where all the primes that divide it are no more than x to the epsilon. And I have no clue why he's asking this question. So this epsilon is some number which goes from 1/3 to 2/3, and so on, and he writes down formulas for what this asymptotic should be. And once he writes it down, it's very easy to see what he has in mind. So the and so on at the end is completely clear. So if you know the question and if you know the shape of the answer, it's completely clear what he means when he says and so on. This is a problem called the problem of finding smooth numbers, so numbers up to x, all of whose prime factors are less than pi. It was something done by Dickman in 1930, and he found a formula for this. He had a little bit more to the shape of the answer, which Ramanujan, it's not clear from Ramanujan's writing, but it's interesting that, of a dozen years before, Ramanujan somehow looked at the same problem, and I don't quite know why. I think I want to mention these two on the previous slides as examples of his insight into mathematics, which meant that he was always able to ask questions which were somehow the right question to ask. And that's not something that's appreciated as much. I mean, people think of the genius of his, of writing down identities, which are very complicated and so on, but he had a nose for exactly what the right question was. I think that's hard to explain.